I'm a professor from Beijing Institute of Nanoenergy and Nanosystems, Chinese Academy of Sciences. I'm very honored to be the moderator of this talk and discussion. Today, we are going to have our 202nd talk, and the keynote speaker is Professor Yamin LEPRINCE-WANG from University Gustave, Eiffel, France. And we also have two speakers and one panelist for presentation and discussions today. First, please allow me to introduce our first speaker today. Professor Yamin LEPRINCE-WANG is a professor at the Gustave Eiffel University, France, where she is the head of the Materials Science and Engineering master degree course. Her main research interest consists of synthesis and characterizations of one-dimension and two-dimension oxide nanomaterials and their applications in energy and environmental fields, such as the nanogenerator of electricity, solar cells, chemical sensors, and water-air purification using photocatalysis process. She received a bachelor degree from Zhejiang University in China, master and a PhD degree from University Paris 6 in France. Then joined the UGE in 1995, chief of the Material Science Department between 2006 and 2010, and the leader of the Laboratory Physical Materials Interface between 2008 and 2014. She co-authored more than 120 peer-reviewed papers, 2 books, and 3. Now let's welcome Professor Yamin LEPRINCE-WANG to the stage and give your talk.
May I share my presentation? Yes, thank you for your introduction. So I will show my presentation now.
Yeah, it's okay for your presentation.
Everything is okay? You can see my screen? Yeah, so I will start. So hi, everybody. I am Yamin LEPRINCE-WANG from Gustave Eiffel University in France. Today, I'm very happy and honored to be here. Firstly, I would like to thank my dear friend Alice for her kind and warm invitation. I hope my talk will be up to your expectations. Then I would like to thank Professor Jin and Dr. Gustave to accept to join me today. My talk will focus on the industrial application of zinc oxide-based nanomaterials. So, a very short introduction on our university. Gustave Eiffel is a new national experimental university created since 2020. And UGE is the result of the merging of our old university UPM with a national research institute IFSTA and some grand écoles. This is why our campuses are spread through France on the different cities in Lille, in Nantes, in Lyon, and in Provence. Of course, in the Ile-de-France, we have the campus in the Paris downtown as well as in Versailles, but the main campus is located in Marne Valley, Descartes City. here is the bird's eye view of the Descartes city. And my lab is located in the Lavoisier building here, you can see. And just some picture illustrate the Lavoisier building here. And my lab with hardworking young people. Now, go ahead to the topic. My talk will be started by a general introduction on zinc oxide, very magical materials, following by different cases. Those are my collaboration with some industrial companies through different projects. In other words, it was industrial needs that motivate our fundamental research. Now, let me show you why I love zinc oxide. This is a very long love story over than 20 years. There are more than 20 young people worked with me on zinc oxide nanostructure, forming a big zinc oxide family in Malawi. You can see there some pictures. Maybe you know someone inside. But why zinc oxide nanostructure? Because among various metal oxide materials, zinc oxide presents itself as a multifunctional materials due to its excellent different properties. Zinc oxide nanostructure are widely used for various applications such as solar cell, piezoelectric nanogenerator, bio and chemical sensor. Zinc oxide nanostructure is also an excellent photocatalyst for water and air purification that will be developed in the case 2 and case 3. Don't forget that zinc oxide nanostructure is also an excellent antibacterial and antivirus materials, and Professor Jing will develop this part later. Moreover, the nanostructure owns a large surface area, leading the enhanced property than the bulk materials. It's evident, for example, in the solar cell or in the photocatalysis, the photon absorption, the capacity of the photon absorption is much more important than the bulk materials. And my research team developed several zinc oxide nanostructure synthesis methods with some pioneer works. For example, in 2004, 20 years ago, for the first time, we obtained the zinc oxide nanowire, monocrystalline zinc oxide nanowire at a low temperature via template methods using electrochemical deposition. And another example, in 2013, for the first time, we elucidated why the zinc oxide nanostructure morphology obtained by different research teams had the different morphology. Our results can guide the experimenter. That means if they want to obtain a homogeneous nanowire array, they should cut the seeded substrate only once the growth time temperature have been reached. By using lithography and nano imprint, we can obtain those beautiful microstructure, but they are less promising for the industrial application due to their very complex, high cost, and time-consuming process. By combining with the electrospinning and the hydro-CMI methods, we can obtain this kind of structure, hierarchical structure, having a very large surface areas. This is very nice application for the gas sensing, for example. Finally, this kind of the zinc oxide nanowire supported by a substrate are more suitable for most applications. So let's see now in detail this kind of the nanowire array synthesis. This is the very simple two-step methods. The first one, a seed layer has been spin coated or deep coated on a substrate, and after the formation of the nanoseeds by annealing, the nanowire array can be grown on it. And I put this here. And here, via those SEM picture, we can obtain, using this very simple method, a very nice, very homogeneous nanowire array. Both XRD and high resolution TEM showed us the very good crystallinity, and here picture show the very good monocrystallinity, and the band gap value of the zinc oxide can be obtained by the measuring the UV visible spectrum absorption by dot plot methods. Here we find about 3.3 electron volt functional energy of our nanowire obtained by the hydro-CMI. This is a quite low value. That means the visible absorption is good for our nanowire due to there is some impurity inside the nanowire. So I will develop in detail for the microfluidic reactor nanowire direct growth in the case 3. We can also use these methods. And our very simple synthesis method allowed us to obtain the zinc oxide nanowire on the very large scale. Here, for example, on a 4-inch wafer, we can obtain the nanowire here covered on the whole wafer with a very homogeneous structure. But it's not the only advantage of these very simple methods. We can grow the nanowire also on the surface with complex geometry. For example, here, this is the microfluidic chamber application. Nanowire here are grown on a microchamber with micro patterns inside. Here we can see the homogeneous nanowire have been grown in the micro reactor, both on the horizontal and the vertical walls. Now I will start the different cases in the industrial application of our dear zinc oxide nanowire. The case 1. The first case is my collaboration with Dassault Aviation and Thales Aviation. Both are very famous French industrial group in the aeronautic field. But why? One day, the scientific project manager from Thales came knocking on my office door to ask me if I would like to collaborate with them. The story begins with a very sad event. In fact, on the 1st June 2009, an Airbus plane crashed into the sea during the Rio-Paris flight. the discovery of the two black boxes in the spring of 2011 allowed investigators to elucidate how this crash unfolded. In fact, there was no technical problem, neither the pilot error. What happened? The starting point of the accident was the obstruction of the piton sensors by ice crystals. These sensors installed at the front of the plane are used to measure the speed of the aircraft. However, their freezing caused a breakdown in the data display in the plane, as well as the disconnection of the autopilot. This is why the three pilots didn't at the first time detect the speed loss of the plane, and they didn't understand the situation after it's too late to get the plane back into the sky. So this accident led the research at the Dassault and Thales Aviation to reflect on their design of the sensor on Airbus. Their objective is to increase the sensor number of the plane. For example, 1,000 sensors on the A380, including, of course, the different kind of sensor, meteorological, environmental, physical, chemical, mechanical sensor, and so on. The project LECAP in French, that means the multifunctional, autonomous, and programmable sensors, was born in this context. Or the mission of our project is to realize an all-in-one sensor with a volume about 1 cubic centimeters, very small. And this schema in the different part. You know, today the multifunctional MEMS sensor to detect the environment, physical, chemical are very easy and cheaper to realize. And the wireless communication is also okay. It's easy to do. And with the very small, both two are very small volume. But here we have a problem. Only problem is the energy harvesting, storage, and the management in this very small scale. This should be developed. And the particular situation on a plane is that we cannot use the solar energy because the most long-haul aircraft fly at night. What is not lacking in an airplane in flight? Yes, it's vibration. So to convert the mechanical energy to electrical energy is the key to power the autonomous sensors on airplane. This is why Dassault Aviation asked me to collaborate with them, knowing that I have worked on piezoelectric zinc oxide nanowire for several years, especially with low-cost manufacturing methods. This is a very important point if you want to collaborate with industrial partner. So, our nanowire-based piezo nanogenerator device fabrication is quite simple. After a spin coat of the PMMA protection and the wire bonding connection, the device is less than 1 centimeter square on area and less than the 1 millimeter in thickness. Thus, we have fully met the dimensional specifications set by industrial partner and to test their performance both under the shaker, that means in the compressive stress, and on a vibrating port or device give a good performance. I would like to highlight that the maximal output is placed between 500 and 1000 Hz. It's in perfect harmony with the maximal vibration frequency on a plane in flight. It was rather a surprise for us. We didn't do any simulation before those tests. In fact, this is a very complex system, including not only the nanowire, but also the seed layer, the substrate, the PMMA protection, and packaging, and wire connection, and so on. So we were very happy to obtain those results. Our industrial partner also. During the 4 years of the recap contract, we have done multiple tests of different sensors with our industrial partners. But the last test in flight have been done after this legal duration of the 4 years due to the long governmental authorization process. So I cannot share with you the more information on the last test. Now, I will moving to the second case. The second case is my collaboration with Eiffel. You know Eiffel here. Eiffel is the company. Eiffel company is the one of the European leader in the construction and the concessions. Before start this project, first of all, I would like to give some words on the state of the art. You know, nowadays the pollutant source are multiplying. A very huge quantity of the organic pollutant issued from the different activities, human activities, is found in wastewater. On the other hand, here, the air pollution from traffic is also main pollution source in the urban areas. The impact of those pollutions on the environment and on the human health becomes critical due to their drastic consequence on the water and the air quality. Both are vital for our life. Facing those problems, it's urgent to find a new solution having low cost, no toxic, environmentally friendly features. So, you know, the water and the food water, the air purification by oxide semiconductor based on photocatalysis could be a very promising way. In our research team, we use the zinc oxide nanostructure as the photocatalyst. You know, the conventional water purification and air purification methods could be very energy consuming or the resulting secondary pollution such as the filters. Now let's see in the photocatalysis case. In general, when the semiconductor is irradiated by light with a photon energy that matches or exceeds the semiconductor band gap, the electrons can be excited from the valence band to the conduction band. at the same time leaving the same number of the holes in the valence band. Both the electron and the hole can produce the free radicals, and those via photoreduction and photooxidation. And those finally, those free radicals owing very strong oxidation power can lead the decomposition of the organic substance to no toxic, very small molecules. Photocatalysis process is similar to the photosynthesis. So we could the photocatalysis could be considered as a green method. To solve the air pollution from traffic in the urban areas, we proposed the depolluting load in I-Street project. This project for the new generation road, we called the fifth generation road in France by using photocatalytic property of the zinc oxide nanostructure. Of course, the 5G road, including many new technology, innovative technology, the depolluting function is the one of those technology including this project. It is a very huge project, collaboration with the Eiffel and the Total companies, funded by the ADEME, it's a very large funding, national funding in France. Talk about the depolluting load. It exists already before us, but you can see in Europe those kind of the depolluting load. It's evident that the infrastructure are not sustainable. It's not good for environment. I don't want to mention their names. And what is our concept, our proposition is here. Our concept is to functionalize the structure, construction materials surface via direct growth of the zinc oxide nanostructure. Thus, we can purify the air from pollution source directly and make the low surface with a self-cleaning function. At the same time, we can reduce the soil pollution. It's very good. So when I first thought to doing this, my colleague considered me crazy, but I don't care. I would like to be the first person who dares to eat the crab, as Chinese saying. So, no sooner said than done. I asked my husband to help me to cut some concrete pavement and here the floor tiles in a small piece. After overcoming the difficulty of adapting those roughness. So there are many conditions to optimize for the nanowire growth. And for the first time, we have successfully obtained the very beautiful zinc oxide nanostructure on those materials you can see here. And this is worth obtaining an international patent. This is a number. Those construction materials decorated by zinc oxide nanostructure showed an excellent photocatalytic efficiency and both under the UV and the solar light. The question was how to scale up. To scale up, we buy a large autoclave and we can synthesize here the commercial photo directly, and a large quantity of the here the some here the what are they logs aggregates for load and bitumen load, and this is for the wall. You can see, and we have tested those innovative materials in a large scale condition. In some city named here, this very large building. This is Sun City as an unique infrastructure in Europe. This is situated in our university, Gustave Eiffel University. This is a climatic chamber of the 400 meters square with total atmosphere control such as the temperature, humidity, running, sunlight, and so on. There are two small cities. The building can be moved from one to the other. And on picture we can see I used a real car to create the pollution situation. In the new situation, and used or this panel, the functionalizer, and also functionalized by the zinc oxide with a rigor of measurement protocol. We can see this is the one of the results. The NOx gas concentration can be decreased faster with the zinc oxide than the natural dispersion. So we can see by using our innovative materials, we can, of course, reduce the traffic pollution in the air. Just one thing I wait, and I hope the investigate from the government to elaborate a new road or a highway for all surface will be covered with the zinc oxide nanostructure. And the mechanical testing has been done also. I have no time to detail them. Move to in case 3. How fluoride microtron? You know, for the water purification, this kind of the classical methods in the static on the dynamic mode to devolute the organic dye in the water. There are many research groups do this kind of experiments. They are very is here we can see the peak of each dye could be decreased as a function with the time the year duration. Of course, we can for example, for this those two organic dye, we can obtain the 100% degradation, but they are time-consuming process. We can see for a very little quantity, we need 2 or 3 hours to obtain 100% degradation. So this is why, because in this situation or decision is better, the pollutant molecule is far away from the semiconductor surface. And so to resolve this problem and improve the photocatalysis efficiency, we fabricate the microfluidic system with the zinc oxide nanowire integrated. In this case, due to the confined medium, we have the easy mass transfer of the pollutant molecule to the semiconductor surface. And so the results show us that they are very, very good. We have a drastic reduction of the photo degradation time from 2-3 hours for the here, 7 minutes for the same quantity. By the way, I would like to thank Professor Jin to help me to realize those microfluidic chamber during his stay in Paris in ESPCI. But you know, this kind of the microfluidic chamber have a flow rate problem. The low flow rate and the high pressure is the general problem in this kind of the small microfluidic system, classic. But in other words, with the very high pressure, will weaken the microfluidic and therefore reduce its durability. But when there is problem, there is always a solution. The solution is the high flow rate, low pressure microfluidic system. In collaboration with the EdenTech, we proposed a new and innovative design for microfluidic cell, which possess a high flow rate capacity working at the low pressure. This is a picture. Here, for the first concept, we do the 3 in and the 6 out. This is the test of liquid. You can see here, the liquid can pass quickly and easily and well out, and here to issue up. And of course, we can treat with this kind of the chip, just one chip, the 115 liter by day. This is the good quantity to negotiate with your industrial partner. By the way, Emmanuel Hua, here, CEO of the EdenTech company. He was my first PhD student long back ago. And then Nathan, the PhD student, worked on this project, was hired by EdenTech after his PhD. And now I will show you in this kind of the microfluidic chamber, we can use the direct growth methods. We can obtain the very beautiful nanowire inside, and the test of the photocatalytic performance here show you we reduce the few minutes in the classical microfluidic to here 14 seconds with the 4 pass, each pass during 10 seconds. So, and by the way, I would like to let you know this kind of the microfluidic chamber using the flex beam polymer fabricated by the EdenTech. Their fabrication doesn't need the clean room. It's very cheap, very easy to do. And now the EdenTech collaborated with the Swiss. Swiss is the first bigger company for the water management, water treatment. To increase the treat volume, they used a package of the ditch and up to the 15 liter by day. So EdenTech told me microfluidics where all the magic happens. To summarize my talk, I would like to do a comparison. You know, in the semiconductor, if the electron with energy larger than the band gap, the electrons can spread over from a less fluid medium to a free medium conduction line. And while for the fundamental research, experimental, if you want to go to the application for the design, device, prototype, industrial scale, you need the knowledge, motivation, energy, innovative idea, and also, of course, funding. So I would like to thank all my young students and all my collaborators. Thank you for your attention.
Okay, thank you very much, Professor Wang, for your wonderful talk. And you have introduced the many applications about the thin-side or based oxide. I think as my research interest at micro energy, so I think the audience such like me will feel very warm to watching your presentation, because the nanogenerator is birthed from the single oxide in 2006.
That's only one. Yes.
Yeah. Thank you very much for your talk. And you can have a rest for a while, and we can move to the second speaker. Now, please allow me to introduce the second speaker, Dr. Yamin. I introduce Yamin is an associate professor in process engineering applied to the environment at Gustave Eiffel University since September 2020. He defended his PhD on September 7, 2016. He was a postdoctoral researcher in Xi'an Jiaotong University in China, lectured in Sorbonne University from 2019 to 2020. He's the head of the process engineering bachelor degree course. He gained experts in multi-scale investigation of bubble drop solid interactions, studying hydrodynamics and gas-liquid mass transfer in gas-liquid solid three-phase systems. His research involved the use of sophisticated optical equipment, such as ultra-fast cameras, capturing up to 2 billion frames per second, combined with colorimetric techniques in various laboratories in China, France, and Morocco. He was awarded by the International Fellowship of Excellence from the government of Japan and Morocco. Additionally, he coordinates 2 research projects and co-authorships 14 papers at top international journals in the field of chemical engineering, fluid mechanics, and environment engineering, and attended 14 international conferences. Now, let's welcome Dr. Yamin to this stage and give your talk.
Thank you. Let me share the. Is it okay? Do you see my?
Yeah. Okay.
Thank you very much for the presentation. I would like to thank all the iCANX talks organizers for this opportunity. And would like also Professor Yamin LEPRINCE-WANG for her invitation to this talk. It will be it will be short, about 15 minutes, but I will present all my works, research in my previous work in Xi'an Jiaotong and also here in France. So I will talk about hydrodynamics and gas-liquid mass transfer around bubbles, usually encountered in gas-liquid solid reactors, and mostly used for water and wastewater treatment. So I am Dr. Abdelrahman Kharbesh. I'm associate professor in University Gustave Eiffel. I have like a PhD in engineering science, mostly in chemical engineering for the environment. And I defended my PhD in the 7th of September. It's the anniversary, actually, tomorrow is the anniversary of my defense date of my PhD. And I did my studies in Morocco. And then I did my PhD between France and Morocco. And then I joined Xi'an University for a postdoc, as a postdoc. And I joined Sorbonne University for my as a lecturer, and then I'm an associate professor here in University Gustave Eiffel. So if I resume and give a summary of my research, you can see that it's a multi-scale research from pilot scale or from the global scale to the scale of a bubble or a drop. So I started my previous research studying and is interested in wastewater treatment. And then processes that can treat wastewater. And in my PhD, I was working on a pilot scale of let's call it a biofilter. So biofilter is a system, is a column filled with the solid particles. And then within, we have some biofilm that treat wastewater biologically. So for this bacteria, we have to provide oxygen. And here we do bubbling to provide air bubbles inside the system. And these air bubbles are the source of oxygen. So oxygen will transfer from bubbles to the liquid, so that bacteria that is in charge of water purification can consume this oxygen from liquid phase, and then consume also or degrade pollution. But when we are studying this, we observed that bubbles are the main important thing in our system. Mostly bubble solid interactions. So we are getting interested in bubble solid interaction and how oxygen can transfer from bubble to liquid. And then in my postdoc, it was like the fundamental thing is how bubble interact with solid, how liquid drop interact with solid, and how it affect hydrodynamics and mass transfer. And then I did some experience in surface treatment and solid surface treatment. So I will talk in this lecture mainly about bubble solid interaction. So let's talk about the system. Let's say that a biofilter is a gas liquid solid reactor. So if we see what happens inside the system, we have solid particles, and we have a lot, millions and billions of bubbles migrating from or rising inside the system between the solid particles. So if we want to study hydrodynamics and mass transfer inside the system, it's possible, but it's not that accurate if we want to understand what happens when bubbles interact with solid particles. So here, a small video of a bubble, and we have some behaviors of coalescence of a bubble that will coalesce and then go to another step in the system. So if we look in this phenomena in a local scale or in a cell, we will see something very interesting. So we will have bubble-solid interactions that are key in GLS, or gas-liquid-solid reactors performance, mostly in mass transfer performance, gas-liquid mass transfer performance. So we have like, if we see bubbles interacting with solid particles, most of the authors can say that it increases mass transfer, it extends bubble residence time inside the system, it increases interfacial area between bubble and the liquid, and it's very interesting in if it's a chemical reactor. So so here, if we see what happens, we can see that there are different types of bubble-solid interactions. And if we observe with a camera what happens, we can say that there is 3 main types of bubble-solid interaction inside a gas-liquid-solid reactor. We can see that there is 3 main types. There is bubbles that are rising near a wall or near solid surface, a vertical solid surface. We can see also, if we see in camera, we can see also bubbles that are confined between solid particles, 2 solid particles. Or we can see also a lot of bubbles that are sliding underneath solid particles. So the question here is how transferred oxygen from bubbles will grow around the bubbles for these 3 types of bubble-solid interaction. So this is the main question. So what we will present here is that those 3 main behaviors, we can say, and we will investigate the hydrodynamics around bubble-solid interactions. We will visualize the oxygen concentration fields around bubbles, and we will see how to quantify this gas-liquid mass transfer around bubbles when they are interacting with solid surfaces. So let's get back to our system. So if we see what happens in the local scale, we will see that when bubbles is rising between solid particles, and there are 3 main behaviors. So if we want to study these behaviors, we have to reduce the complexity of the system and control its complexity. So the main, if we want to understand the physical phenomena and how mass transfer occur here, we will say that having bubbles near to plane surface is the most interesting case to study. So we have 3 main cases. We have the bubble rising near a vertical wall, solid wall, and how hydrodynamics and mass transfer will occur here or will involve. And the second one is confining bubbles with between parallel walls. So here we can change this distance and see what happens in the hydrodynamics and gas-liquid mass transfer. And the third situation is the sliding bubble. So if we put a bubble and let it slide inside a wall, how oxygen will go inside the liquid and how it will involve inside the liquid. So let's to study these situations, the main important thing is to reduce the scale and to study the bubble inside, let's call it LHO cell. So LHO cell is a cell that bubble is fixed in the 2D. It's a quasi 2D experiment where bubble will be injected here, and we will use high-speed camera to observe what happens in hydrodynamics and mass transfer. So the dimension, we use a lot of helical cells that are sometimes bigger than these dimensions. And we used also the same thickness of the cell, and we used different equivalent diameter of bubbles from 4 to 10 millimeters. We can go under 4 millimeters. We can produce 1 or 2 millimeters, and then for camera, let's say that we have a frame rate of camera about 1,000 frames per second. It was sufficient to observe what happens. So this is the 3 situations we can say, and then we have a bubble and a solid surface, and we change the angle of the inclination of this surface, or the distance between the center and the solid surface, center of bubble and solid surface. So we have the 3 main situations: a near wall bubble, a bubble rising between 2 parallel walls, and then the effect of wall inclination on sliding bubble hydrodynamics and liquid mass transfer. So let's say the first part of this situation of the first behavior, the near wall bubble. So the near wall bubble, we fixed the equivalent diameter of the bubble as 3 millimeter, about 3 millimeter, 3.65 millimeter, and we variate this distance, the center of the bubble, from the surface of the solid wall. So we begin with 1 solid wall. We have a camera, a backlight, and a computer that can manage the camera and operation control of air compressed air. So let's say the first thing is that the reference, the free rising bubbles. If we have a bubble of 3 millimeter, we have an ellipsoidal bubble. So the rising of the ellipsoidal bubble is a rising, is a zigzag rising. It's like a curve. If we see its velocity, its trajectory is like a sinusoidal trajectory. It's like zigzagging trajectory. And if we see velocities from the x and y, we have also some variation, sinusoidal variation of the velocity from x and y. And the formation of the bubble also follow this behavior, and also the inclination angle of the main diameter of the bubble. So if we put this time, if we put the solid surface near the rising bubble, we will see what we will see is that the rising bubble will migrate from the wall and go far from the solid surface, and there is an inclination angle depending of this factor, which is the distance between the center of the bubble and the surface of the wall. So we will see that for this situation, bubble will migrate from near wall to far from the wall. And then there is an angle of migration. And this angle of migration, you can see several situations here. And then if we put the wall near the bubble, we will see that there is an inclination and migration of the bubble from the wall. And the angle of migration will increase dependent on the initial distance s from the wall. And if we see the frequency of oscillation and the amplitude of oscillation didn't change too much. If we put 1 wall near the bubble. If we do a force balance, we can see that it follows the velocity and buoyancy force, drag force, and lift force will follow this trajectory of the bubble and this distance, and it will depend on the distance from the wall. Now, all of these situations, we had like only the dynamics of the bubble. So if we want to see the flow structure, what we used was like flakes, micro flakes that are micrometric dimensions with a density relatively equal to water, and that these flakes reflect the light. So if we put like a bubble rising near a wall, we will see something like this, and we can see the flow structure in the wake of the bubble. And then after that, if we play with the light, we can see clearly the flow structure underneath the bubble and in the wake of the bubble, and we can see the orientation of the flakes inside the liquid.
Dr. Kircher, please aware the time.
Okay, I will go fast. After that, we will present the bubble confinement between two walls. So it's the same thing and different distances. So in this time we have like different kind of bubbles. So from small bubbles of 2 millimeters to 15 millimeters of equivalent diameter. And the trajectory is different here. So we will use like a dye to observe oxygen transferred from the bubble to the liquid. And we will make like image processing in MATLAB to see what happens and how to quantify oxygen transferred from gas to liquid. So here we have like different situation. So here, if we make the make the image processing, we can quantify oxygen transferred inside the liquid, and depending on the confinement of two walls. So you can see that it depends on the trajectory, on the distance between the two walls, and we can see oxygen transfer here. We can see how oxygen is transferred from the bubble to the liquid with a colorful way. So here is different kind of oxygen transfer and different size of bubbles, and we can quantify the oxygen concentration, and the final type of behavior is the sliding bubble. So the same thing is like we will put like inside the cell a sliding bubble, and then we will see what happens. So here is a sliding bubble transferring oxygen from gas to liquid, and in the pink color we have oxygen, more concentration of oxygen. So with the image processing procedure, we can quantify oxygen transfer, and finally we can better analyze oxygen transfer from gas to liquid. We can observe there is a near wake where a recirculation zone enclosed by a counterclockwise single vortex leg, where oxygen is transferred, and then depending on the angles and on the bubble side, we will have different situations. We can discuss this in the discussion parts. So here we can quantify all of the mass flow of oxygen and so on, and we can make modelization and compare the sliding bubbles with free rising bubbles and make like more accuracy on the existing models. So what's next is like we will continue on this subject with collaboration with co-supervising PhD thesis with Professor Yamin LEPRINCE-WANG. And I thank you, and sorry for this this late. I thank all the people which were involved in all these aspects of hydrodynamics and mass transfer of bubble interactions. So thank you very much, and sorry if I was a bit late.
Okay, thank you, Dr. Kircher. A very interesting work and a wonderful talk for investigating the behavior of bubble on the solid surface. Okay, you can stop your screen.
Okay.
Okay, let's move to the third speaker, Professor Guang Yingjing from West University, Xi'an, China. Guang Yingjing is a professor at the School of Physicals, specializing in soft matter physicals, biophysicals, and their medical applications. He earned his behaviors degree from Sanya University in 2002 and his PhD from the School of Physicals at Peking University in 2007. He then conducted postdoctoral research at ESPCI Paris and the Paris Sud University. In 2009, Dr. Jin joined the School of Physicals at Northwest University, where he established the Soft Matter Physicals Laboratory. He currently served as the director of the Department of Materials Physicals. Dr. Jin's research focused on active matter, self-propelled microswimmers, connective behavior, and their biomedical applications. He is also part of a joint research team selected for the Sino-French Scientific Research Partnership Program. To date, Professor Jin has published over 18 peer-reviewed articles. So now let's welcome Professor Jin to the stage and give your talk.
Okay, so the slide can be seen.
Yes.
Okay, so thank you. Yeah, so first of all, I thank Professor Zhang Haixia for this iCANX talks platform, and also the chair by Professor Zhang Chi. And also I thank Professor Yamin Wang for the invitation to let me to speak here. So my title is here is like I will talk about the special applications of the zinc oxide nanomaterials. So I have a background of physics. So talk about discussing about microorganism, particularly in bacteria, is not so usual. But in recent years, so we found that these tiny creatures are incredibly interesting. So from the physics perspectives, so we know the bacteria is the oldest life form on the Earth. For example, they appear about around 2 or 3 million years ago, which is much longer than our human beings. And these bacteria are, could be good or bad. So we need bacteria, for example, in our gut to digest or extract the nutrition from food. So now it's a popular topic about the gut bacteria. But we have the experience. For example, we always link the bacteria with the, let's say, the diseases or health. It seems that the bacteria can make some infections, and with these infections, so they need to find surfaces. So we live with these bacteria, and they are surrounding us. For example, as shown in these pictures, so the bacteria live in a fluid environment, like liquid or air, and they can attach to the, let's say, the surface of the bottle and the seabed, or even liquid and air interface, or the rocks, and even in the soil. And also they can attach let's say to the other organism, the surface, for example, the plant surface, or even animal surface. And we also found the bacteria or the microorganism on the rocks or concrete. For example, here, this is the picture, a beautiful monument, but we can see there's some colorful stuff. And this is also we call it the bacteria, or like biofilms. So more importantly, so we have the experience that the bacteria can cause some infections, which we found the problems in our body. For example, they can form the biofilms, and this biofilm is not like a simple films, which with the bacteria, they build these communities with a matrix and produce a lot of stuff or substance. And with this community, the bacteria can protect themselves against the drug, for example, the antibiotics. So that's why we have these global troubles and concerns about the antibiotics troubles. And these biofilms, so it is interesting that, so I found this term biofilm from the biological film was used firstly in the paper, and talk about the wastewater purifications, which is irrelevant with the topics by Professor Wang. And basically, so in these biofilms, there's two important issues. The first one is the bacteria can swim, that we call that the motility, the ability to move themselves. And also, they need to find a way to attach the surface, and there they build a community. And with this community, they can protect themselves. So that's why, and the bacteria use the motility and attachment on the surface to cause a lot of problems. So then we try to figure out how they can move, or what is the bacteria's locomotions. So here are some mechanisms for the locomotion. For example, one type of the bacteria, they use a helical flagellum, and this flagellum can be rotated and push the body forward, and then they can move to looking for food or escape from the dangerous situations. And there's another one, like they use a very small filament to deform and do the retraction process, and then this retraction can push their body to do the movement. And also, if we could look at this tiny guy, and they can use, let's say, this is a sela, or like also flagellum, and to synchronize this movement and let us swimming in the water. And also, even they can use more sela to do a very special movement in the liquid. So all of these bacteria or microorganisms to find ways to move them. And there's a special one, for example, here, like, so we use a model bacteria as an E. coli. They use the rotating helical flagellum. So if we look at this picture, so this is the flagellum, and there's a motor cross the membrane of the cell, and this motor has a rotator. This is the rotator, and also their stators. And these stators and the rotators connect a very long flagellum. This flagellum has a diameter of like 20 nanometers and up to a length of 10 microns, which connected to the motor by a flexible hook. So this is a very ingenious model. I would say it's amazing. In the nanoscales, we call that a nano robot, so that we check out the size. So it is the total size could be 45 nanometers. So it is amazing. And with this flagellum, you can swim on the surface. So here we took this video where we can say the bacteria. So the spot, the red spot is a bacterial. They do circular motion on the surface. And this phenomena was first found in, let's say, 1970s. And 30 years later, the mechanism for this circular motion was proposed. And also later, there's some physical models to interpret this circular motion. But in general, so this circular motion can trap the bacteria onto the surface. And there's another famous phenomena that the bacteria can attach to the wall or to the surface. So here, for example, is a channel. This is the bottom, and this is the top. And the bacteria can escape from the bulk liquid and to go attached to the walls. That make the population of the bacteria is much higher than the case in the bulk. And there's a lot of beautiful works to explain the mechanism of this accumulation at the wall. And even this accumulation can happen in a simple liquid and also in the complex fluid. For example, this result is from Yamin from Hong Kong. And they found that the bacteria has a higher concentrations on the surface in the polymer solutions. And it's more interesting. So we think about maybe we can use a flow to wash of the bacteria away from the wall. But the bad news is that we cannot wash them out to drive them away from the wall. For example, in 2015, there's a nice paper. They found that they use the shear flow in the channel. So here is the wall, and this is another wall. So we can say most of the bacteria go to the side wall or go to the walls. So that make the accumulation of the bacteria due to the fluid dynamics mechanisms. And also, so they can do another interesting phenomena on the surface. So the bacteria can do the upstream. That means they can swim against the flow in the opposite direction of the flow. And even worse, they can do much faster to contaminate, for example, from here to the fresh waters. So which we call that a super contamination found by the Eric Lemos group in Paris. And also in recent years, we found maybe there's another mechanism to explain the bacteria can do the drift motions. So they can here, for example, we can try. So the bacteria, for example, this is the flow direction, but they can go the side walls with the deviation from the stream lines, which is very interesting and abnormal. And we developed a model to explain this phenomena. So, okay, so let's say, so it is clear that the bacteria are trapped and accumulated on the walls, which is due to the fact of the fluid mechanisms instead of the bio or chemical reactions. And also, if we want to remove the bacteria from the surface, it would be very challenging. And then, so let's say go back to the zinc oxide of the topic in this talk. So what we can do by the zinc oxide nanomaterials, can we do something to, let's say, to treat this bacterial attachment on the surface? So the answer is yes. So since that the zinc oxide nanomaterials can coat on the surface to change the charge, weathability, roughness, and topologies, or even stiffness. And all of these factors can do some sense to let's say, to change the behavior or even the attachment of the bacteria on the surface. And we all know, so it is easy to generate some ions or charges in by the zinc oxide. And also we change the weathabilities. It is easy. And of course, the morphology. So this is the famous pictures by Wang Zhongling. And in our results, we found it is not so difficult to fabricate the softness of the nanostructures with the combination of the oil and the nanostructures. We will come back to this point later. So firstly, we try to figure out, is it possible to change the wettability of the surface by coating a zinc oxide nanoreels? So it's not so difficult, but unfortunately, we found that the residence time of the bacteria on the surface cannot be changed when we change the wettability of the surface. And also, the bacteria is happily to do the circular motion on the hydrophobic surface, which is very interesting and we cannot understand at the moment. And then, so with the help of the flow, we can wash away the bacteria deposit from the surface? So the answer is also yes. And let me skip the details. And also, if we introduce the UV illumination, and we can slow down the bacteria swimming on the nanostructures, and here so we can say the speed go down to almost to zero within, let's say, 10 minutes. So which give us a very good way to control or capture the bacteria onto the surface. But it could be confusing that here, so we need less residence time, but here we have could be infinite residence time, since that the bacteria are trapped or catched on the surface. But we can use it in another way to fabricate devices to capture the bacteria and then to do the filters in the tubing devices. Okay, so there are another questions we could ask. Let's say intuitively, the nanomaterials of the zinc oxide could be very sharp nanotips. So it is possible we use this nanotip to just puncture or destroy the bacteria's soft body directly. Okay, yes. So the answer is also yes. So there's a report, not by us. So they change, let's say, the sharpness of the tips, and finally, so we can say these sharp nanotips directly break the membrane of the bacteria. So that means we kill the bacteria directly just by physics. And so far so good. So all of this we talk about was by physics. So it is possible we can use chemical reactions. So also there are two mechanisms to use the chemical interactions between the nano materials of zinc oxide with the bacteria. So for example, if the nanoparticles or nanowells, of course, they can go inside the bacteria, then there are some chemical reactions to damage the proteins or DNAs. That means the bacteria can be killed by these reactions. And also there's another mechanism. If the bacteria swim on the, let's say, films or nanowells or nanoarrays, that means the nanomaterials cannot go inside the bacteria. But we have another solutions. So this generate the zinc oxide can generate the zinc ions, and also the hydrogen peroxide H2O2. Both of them can destroy the bacteria directly. So we have a lot of things to do with these chemical reactions, but it's not it's out of the scope in our researches. So let's say, so with these brief introductions, so we also learn from the Professor Wang's talk. So the zinc oxide, the nanomaterials can be used in industry, include air pollution, water pollution. But water pollution, we have to think about the contamination from the bacteria, and which is the form of the biofilms. Is dangerous to cause some diseases for the clinical treatment. So that's why we focus these parts by the zinc oxide applications in the contamination. So with a unique techniques here, so we have a 3D tracking system to follow each bacteria with a very high speed and high resolution to have these trajectories of the bacteria, which allow us to understand the locomotion mechanism of the bacteria. And also we can track these bacteria in the complex environment, for example, in biofluid, like a blood vessel or blood streams. and also check them in the polymer solution or mucus or even in our bodies. And also we can develop some versatile devices with microfluidic traps and use a lot of geometry to confine or catch the bacteria to do some, let's say, the filter things from the tubing applications. And even we can go down to the molecular size to understand how the bacteria use the flagellum to rotate with a very high speed at a very small size. At this kind of scale, we can recover the mechanism of the locomotions. So I would like to say, so this lab testing or this understanding to help us advance the understanding for the locomotion mechanism. And we can believe that it could promote some new applications in, let's say, biomedicals or bio contaminations. So with this, I thank my teams and also the help from doctors in hospital and collaborators from medical school and from a physics department, particularly Professor Wang, to introduce me into this kind of applications from zinc oxide. So finally, I thank you for your attention.
Okay, thank you, Professor Jin, for your great work on the zinc oxide nanomaterials and some new applications. Okay, now we have finished the three presentations, and now we can move to the discussion. I will introduce the panelist of today's panelist. Dr. Yu Song from City University of Hong Kong. Dr. Yu Song is currently a president as assistant professor of biomedical engineering at City University of Hong Kong. Before joining City University, he was a postdoc scholar in Professor Wei Zhao's group at Caltech, and he received his PhD degree at Peking University under supervision of Professor Haixia Zhang. His research interests focused on bioelectronics, where sensors, advanced manufacturing, and digital medical to achieve wearable bioelectronics for personal health. In the related fields, he has course over 17 publications on the Science Nature Index sister journals, very famous journals. Dr. Song has been recognized as the world's top 2% scientists and received 13 awards. And welcome, Song. Okay, now let's welcome all the speakers and the panelists to the stage. Okay, Dr. Yu Song, as the only panelist, and you may ask your question.
Yeah, thanks
first.
for the introduction from Professor Zhang. Actually, I also have the same feeling like when I look at the zinc oxide, because we are all like work on some nanogenerators before. So I actually have a very general question for both Professor Wang and Professor Jin. So I know that the zinc oxide has been researched for several years, and in the beginning, some people might work on some energy harvesting part. So how do you feel about the future specs or the research directions of this field? Do you have some other suggestions of thinking about what could it work or has other potential? I know you all present some potential applications of this zinc oxide, and also I feel maybe another strategy is to combine the zinc oxide with some other functional materials to utilize the advantage of zinc oxide with high surface area or other properties. So yeah, actually the first is about very general question for both professors. Yeah, thank you.
Thank you very much for this very interesting question. Yes, it's a very large general question. Of course, zinc oxide materials, for me, this is a magical materials. But honestly, I think for the potential and the future application, the doping, the functionalization, and combining with the other nanomaterials, I think is the main way for the successful application. Because zinc oxide alone on some old defaults. For example, zinc oxide cannot support the very low pH or very high pH. Zinc oxide can support the pH if my memory is good from 5 to 9 is okay. Our test showed the or application conditions in the air, in the water, but lower than 4 or more than 9 in the pH value, zinc oxide can be dissolved. Look, there is the Gaussian on the surface. Even this is the ceramic oxide materials, but the zinc oxide alone is very not very robust, I think. So I think the doping or combined with other materials is a good thing to do when you think about some application. For example, for our application, photocatalysis, we with as a PhD student line, we use the ALD method to coating the zinc oxide with a very, very thin TiO2. Because TiO2 is very robust. In the very large pH value, we tested TiO2. Okay. So, but if we cover the zinc oxide by full TiO2, we reduce the photocatalysis efficiency. This is one thing. And other research topic, we do the doping. When zinc oxide doped with the other metallic elements, such as silver or iron, those are the very biocompatible elements, we found that the corrosion phenomenon can be reduced by doping those elements. I think zinc oxide is a really multifunctional materials. But if for each application, that you have to have in your mind is zinc oxide in the which medium when you use your application. It's a very huge environment. Maybe it's better to protect the zinc oxide for the sustainability and the durability.
Okay,
I
yes,
think,
thank you.
maybe Professor Ting can add some.
Okay, yes, thank you. Thank you, Professor Song. So this is yes, a big question, I would say. And also I think Professor Wang has a lot of stories about the zinc oxide, so that we start the research from the zinc oxide since in the old time, I would say it's 2000, around 2000. And now less and less researchers to doing work on the zinc oxide. That's why Professor Song used the word like a potential, which means potential. Okay, we need time or we need more to from research to go to the industry. But actually, I was totally convinced by the Professor Wang's talk. So there are a lot of exciting results. I mean, to collaborate with the companies, for example, the air pollution and water pollution. But that's why I would like to suggest that if we integrate this biofiltering or like antibacterial parts, so into air pollution or water pollution, it could be wonderful. I'm not sure, but I focus on the research. But I believe that so the zinc oxide, so it's cheaper and it's easy to control, and even we can do a mass product for these special materials, and also it's functional materials. I think Professor Zhang Zi has a lot of things to share with these materials since you work in a big institute and famous big institute about the zinc oxide also. This is my comments, not a suggestion. Thank you.
Okay, yeah, thanks, Professor Jing. Yeah, I also had another question for Professor Kabache. I know, I mean, the bubble always looks quite interesting for people when we watched about your movies. And actually, the first question is about the, can you do some like the droplet or the bubble control? Like you can control the movement of the bubble with some other like electricity. I'm not quite sure, like electricity or magnetic something, magnets or something other solutions to control the movement of bubble. And also, do you also considering about some, because I'm working on some biomedical engineering, so you also always think about, do you have some other potential ideas like if the bubble can deliver something like with this bubble movement, you can, for example, the drug delivery or other for some biomedical applications. Yeah, thank you.
Thank you very much. Sorry for, I think there is a noise from behind the office. I hope that there is no noise that you.
Yeah, it's
no
good.
noise. That's all. No noise.
There is a noise? No noise?
No noise. Yeah.
Okay. So thank you for the question. Actually, for the experiments we have done, bubble are generated from a capillary and then they go rising freely in the system. So we cannot control them, and we control them only by interaction with solid surfaces near to our bubbles. So the thing is that we try to keep the same condition, but simplified the same condition in industrial reactors. So we generate bubbles, and then we let only Archimedes forces and lift force or buoyancy force rise the bubble and freely rise the bubble, and then study the bubble interactions. There are some studies, I think, that are trying to control bubbles behavior with electrical, magnetic field, and etc. But I'm not in a specialist in this kind of study. But I know that there are a lot of studies that are controlling bubbles. Mostly the bubbles that are in air, like air, liquid film inside air. What we are studying is bubbles, gas bubbles inside liquid. So it's quite difficult to control the behavior with some electricals, and this is. Okay. I hope that I answered the question.
Yeah, thank you. Yeah, that's all for my question. Yeah, Professor Zhang, maybe you can go ahead.
Okay, thank you, Songyu's question. And Professor Jin, do you have any question for the other two speakers?
Okay, thank you for this opportunity. Yes, actually, so I have a question for the other Haman. So it's very interesting. You can see the bubbles to do the zigzag motions inside your channels or inside your capillary. So
Yes.
I'm wondering, so what's the mechanism? It should be like rising, in a straight way.
Exactly.
You have some,
Actually, yeah, it's a very interesting question. So actually, bubbles inside liquid, only bubbles that have diameter less than 1 millimeter, exactly less than 0.7 millimeter, that are spherical and rise rectilinear. Only those bubbles, and also the other kind of bubbles that rise like rectilinear or linear are the most bigger one, is like more than 15 millimeters. All the other bubbles are ellipsoidal and they are rising zigzag. If we observe that in fast cam camera, we can see that actually they are rising zigzag. So in all these situations, ellipsoidal bubble are rising zigzagging inside the system. So why they are zigzagging? Because there are some spherical bubbles are more stable. So they are spherical and rigid. So it's the same pressure that are produced near the bubble. When you increase the diameter of the bubble, it becomes ellipsoidal, and it begins some deformation in the shape of the bubble. And those deformations can generate some instabilities and generate some difference of pressure, and then the bubble starts zigzagging. So we can see in the experiment, it starts rising rectilinear, linear, and then at some point, it starts zigzagging if the bubble is more than 1 millimeter in the diameter. So this is yeah. So most of the bubbles that are like more than 1 millimeter, they are zigzagging actually.
Thank you.
Yeah, welcome.
Thank you, Professor Jin. Have you finished your question?
Yes, I think yes,
Yeah.
So it's interesting for me. I mean, so that we found some bacteria to do the zigzag. We call that a wrinkling or like a wobbling, but it is active one or living stuff. But in your passive bubbles can do this similar trajectories of zigzag. So it's very interesting. I would like to talk with you later. Thank you.
Yeah. Actually, yeah. I will be very happy to talk
Jin, you are welcome. Professor Jin, you are welcome to Gustave Eiffel University.
Exactly.
Okay, thank you.
If you have time, I can invite you to join our university.
We found time to talk.
I think so. You can discuss with Abdelrahman. Yes,
exactly.
Very interesting.
Yeah, you can put some bacteria inside your bubbles. I mean, use as a reactor, as you claim.
Yeah, actually, this is very, very interesting because it can be like, it can act like contaminants at the surface, and then it can reduce mass transfer. I don't know, but actually there are some studies around this subject, and there are like very, very interesting studies studying like if some, like, let's say some dust can go at the surface of the bubble, how mass transfer will grow, and this is one of the most interesting subjects. And actually, it's very, very occurrent in some wastewater treatment reactors, because there are a lot of bacteria, and these bacteria inside the reactor, there are a lot of bubbling, And actually, we want to know if this bacteria reduce the performance of mass transfer or not. So, and if also for biofilm, there are some very interesting subjects around biofilm, like sticking on a wall. And we can talk about that very in a lot of like in a lot of details, because I'm very interested in this subject. What happens when bubble and wall colonized with biofilms? How hydrodynamics and mass transfer will grow if bubble is interacting with a wall already colonized with biofilm. So this is one of the interesting question that can be studied later. So we can discuss that in detail later.
Thank you. I finished all of my question. Thank
you.
you.
Thank you, Dr. Kircher, for your answer in detail. And do you have, Dr. Kircher, do you have any questions for the Professor Jin and Professor Wang?
Yeah, actually, for Professor Jin, I like very much this subject also, but I want to ask one small question. Did you work with different kind of biofilms, or it's already always the same kind? I understand that there are several types of biofilms. There are thick biofilms, there are thin biofilms. What kind of applications you have in your studies, and what kinds of biofilm do you study usually?
Okay, thank you. So yes, so this is a very good question. So the biofilms, so there's a lot of types of the biofilms developed by different bacteria. So we know the bacteria, the species of the bacteria has even more than any cells in our body. So that means they can create different biofilms with different thickness. Thickness is not so important anymore. You know the chemicals, the biological function is much more important. Mm-hmm. And if you how to know if you characterize these physical properties, I think at the moment it's a challenge. So we can use invasive method to measure, for example, the basic variables like elasticity or modulus. Even that is difficult.
Okay.
But that's why they found the chemicals or like a medical treatment to do something on these biofilms. Mm-hmm. But there's a lot of things, so we can learn from the physics perspective, but not from the biological perspective.
Yeah.
Yes.
Yeah. Because in water treatment and wastewater treatment, their thickness is very important because it's for gas, liquid, solid reactors. Thick biofilms can cause clogging.
Yes.
And clogging of the reactors, it means that pores are all full with biofilm, and we have to clean a lot of times our system. So it may be interesting for maybe wastewater treatment applications, but it's very important subject, I think. And it's very important in terms of research questions also.
Agree.
Okay, thank you.
Thank you.
Thank you, Dr. Kircher. And it's my turn to ask questions. And I have learned a lot of single oxide materials from Professor Wang's presentation. Because I first familiar with these nanomaterials that is from Nanogenerator, that is for the energy applications. And today, Professor Wang has introduced many other applications the energy and for the environment. So and my first question is still focused on the micro energy. That is, I see the presentation in Professor Wang. You have give application for the aircraft. That is, you use the synthesized materials as the power in the aircraft. So I'm anxious about the power of the device, the power density or the power device, and is it have the plenty power to power supply for the device, for the sensors? So can you introduce more about these applications?
Thank you. I think this is not the first time when people ask me this question. Each time I present the nanogenerator as the application in the device. Application that I presented with the French companies. Application is just to supply, to power the device by the MEMS, just the micro device. So they need really very, very low power to supply. It's in order than the microwatt and less than the microwatt. So in such case, zinc oxide can be used. But if you need a larger presence, yes, you cannot use such kind of the nanogenerator. So the application, if you have to, so I have not the time to talk about the flexible with based on the PVDF TRFE, another flexible microgenerator. Yes, in such case, we can produce much higher power to supply the device. But zinc oxide is really specific for the vibration only on the aircraft.
Okay.
If in the other way for the another application, if you have the other mechanical force, you can deform the device. Of course, you can use the cheaper, the flexible device, the microgenerator. We can generate the much more the energy. But on the aircraft in flight, there is only the vibration. And we just need this vibration to solidify the zinc oxide nano array to generate the electricity. So in this specific case, the zinc oxide nano array is the best choice. But it's not in the general case in the other application.
Yeah. Maybe on the aircraft, inside nanomaterials can be a skin, just like a skin on the aircraft.
There is many applications, many nanomaterials on the aircraft.
Yes.
For the structure, for the sensor, for the, of course.
Yes. Okay. I have another question about the application for the environment. That is for the photocatalysis, and I think there are many materials can used for the photocatalysis. And what about the advantages of the synthesized nanomaterials? Is it irreplaceable of this subject?
Thank you for your question. This is also a good question. Of course, for the photocatalysis process, the metal oxide semiconductor based the photocatalysis is the one of the kind of the photocatalysis. And among the metal oxide materials, zinc oxide can be compared often with the TiO2, for example. TiO2, the oxide, the titanium. This is also a very good photocatalyst. To be a good photocatalyst, you have the some, I have no time to detail this problem in the scientific form. You have to a larger band gap. If you have the semiconductor just a very small band gap, the electron can be excited and quickly recombined with the hole. So there is no creation of the free radicals. We have to separate the electron and the hole. So we need a large band gap. And the large band gap oxide, there are two best candidates, TiO2 and zinc oxide. Most study in the past used the TiO2. For me, TiO2 have the old very good properties. This is not the problem. But the problem of the TiO2 is the toxicity. The use of the large-scale TiO2 nanoparticle in our environment is very bad. It's not good at all. So compared to TiO2, zinc oxide, the advantage is no toxic and biocompatible. This is why I use the zinc oxide since more than 20 years. You know, before I started TiO2, but not for the photocatalysis. I know very well TiO2, but I don't use TiO2 for the photocatalysis. Because if we would like to protect our environment for the air and the water pollution treatment, we have to use our photocatalyst materials as a no-toxic materials and use the fabrication process as the green process. This is why I usually would like to use zinc oxide and hydro-CMR methods because this is a very low-cost, environmentally friendly method. We cannot obtain the TiO2. Yes, we can obtain the TiO2 nano materials via hydro